All right, well, it's probably as good a time as any. So, yeah, as you can tell by the title, this talk is about the real performance of mobile devices. Now, I actually wasn't expecting to do a talk at GCAP. We ended up being a late sponsor, and as a sponsor, we also have to provide a speaker. So I was asked to come up with a talk, and I thought, I have no idea what to talk about, so maybe failing having anything useful to talk about, I can always come up with an hour of ranting and grinding my axe about the performance of mobile devices, which is basically what you're all in for. We're going to cover a couple of things. I'll ground a few things in history. There will be some debunking of common misconceptions. Hopefully the misconceptions aren't necessarily held by people in this room, but they definitely do exist. I will hopefully bring it back to what we should think about as game developers when we're developing for mobile devices. I'm going to touch a little bit on some of the in vogue high-performance graphics APIs, and I have a slide at the end about VR. I kind of wanted to say more about it, but then I realized I didn't really have all that much to say. So it ended up being one slide. We can talk about it afterwards in the Q&A if anyone's interested. And I'm going to intersperse it with some esoteric architectural information so that hopefully people don't get bored for long periods of time if they have no idea what I'm talking about. So I asked you guys, basically, who you were, and I think it's only fair that I say who I am. So I'm a technical director at EA Firemonkeys. I'm also the engine architect, and those are the three titles that we have out in live service right now. And I've been working in the mobile space since the iPhone 3GS, which is when programmable shaders came out, and that's when things actually started getting interesting. So we'll start with some history. In 1993, the first superscalar CPU was released for the PC, and that was the Pentium. And superscalar CPUs are ones that can execute more than one instruction simultaneously. In 1996, the Pentium MMX invented speculative execution and then branch prediction. We broke the 1 gigahertz boundary in 2000 with the Pentium 3, and the first 64-bit desktop CPU was made in 2003. And you could buy a dual-core Pentium D in 2005, and mainstream quad-core CPUs were available a year later. Now, if we compare this with mobile technology, it's advancing a lot faster. Now, a lot of this is prior work, but the hardware is changing at an incredible pace. In 2007, the original iPhone, which really started this whole smartphone revolution, was released, and it was a very simple ARM11 chip running at 400 megahertz. In 2009, they followed it up with the 3GS, which added superscalar code, SIMD, and speculative execution and branch prediction. Basically, they took the whole group of enhancements that took 6 years or so for desktop CPUs, and they changed their platform in 2 years. A year later, it was possible to buy a dual-core mobile CPU, and they also broke the 1 gigahertz boundary. 2 years after that, you could get a handheld quad-core computing device, and a year later, they thought they'd add another 4 cores. But is this really an accurate picture? When the iPhone 6S was released, Phil Schiller said that it had desktop-class performance. Now, what did he mean? Did he mean this, or did he mean this? And, you know, in addition to the processing power, there's also a question about the graphics power. I found a few very excited, breathless quotes. One saying that the iPhone 5 has full console quality graphics by some guy from EA Firemonkeys. And the iPhone 6 was on par with the PS4 and the Xbox One. Now, neither of them are with us now, so take that as you will. But if you believe these things wholeheartedly, I think you should be asking yourself, why don't mobile games look like this? And is it even possible? So the too long didn't read version of this is no, it's not possible, and sorry. There are two massive limitations with mobile hardware that will always stop your ability to create, for example, Doom 4. The first one is power usage. You know, we want a phone that's small and light and has incredible battery life. The second one is thermal design power, which is closely tied to power usage, but it also limits the sheer amount of work that the chips can do. They are using very similar technology to desktop CPUs, but they have to run in much smaller power envelopes. The iPhone 6s operates at under 4 watts, whereas an i7 laptop CPU is 50 watts. And if you pull in a discrete graphics card, such as the GeForce 980M, another mobile graphics card, so these are already portable ones, that's an additional 122 watts on top of that. And at the end of the day, people just don't want to buy phone radiators, although apparently you can buy them. So if you are a serious phone gamer, then consider DL Extreme. And so, you know, there is ultimately a physics reason for this. There simply is a limit to the amount of work that you can do on the chips with the power requirements that you have. Now, this is a screenshot of the original Infinity Blade, which came out on the iPhone 3GS. And it's kind of interesting because I remember when it was released, everyone was talking about how mobile graphics was already at Xbox 360 levels. It was amazing. I actually went to the GDC talk that Chair did. And Infinity Blade is an exercise in careful design. They only have 2 animated characters, and they're the only things that actually have shaders that are complex. The lighting on the ground is all pre-baked. What you can't see is that all the geometry in the level has been manually removed, the backsides of it, so that the vertex processing never happens. And it only works from this fixed camera angle, and every single scene is a completely different scene because the artists have had to remove different polygons. In addition, almost all of the things beyond kind of 20 meters away are proxy textures that have been pre-rendered. So it's kind of not a fair comparison. So we're going to take it apart and talk about the CPU and then the GPU. Almost all mobile devices use an ARM architecture, which actually comes back from the original BBC Micro when Acorn Soft decided they wanted to get into the chip game. Now, ARM doesn't actually produce the hardware. They just license it to other manufacturers. And then they create their own derived silicon-on-chip systems that have integrated graphics and memory controllers and all sorts of things like that. Now, there are lots of variants because once they've received an ARM license, they basically get the ability to change it however they want. These are just some examples of different ARM architectures that are available with their brand names. Now, there are non-ARM architectures on mobile, but I'm not going to talk about them because thus far, Intel hasn't really worked out how to deal with the space. Can you actually compare an ARM and a desktop CPU? Well, the first thing you need to do is ignore the clock speed. Hopefully most of you, I mean, I'm starting to realize that I'm getting older, remember the megahertz wars of the early 2000s where the Pentium 4 was put up against the Athlon, and people were buying Pentium 4s because the numbers were bigger, because they were running faster, but the Athlon massively outperformed them, and so AMD just stopped publishing megahertz and started producing performance ratings instead. The same thing applies when you're comparing across 2 different architectures. Obviously, I would hope. You can't compare clock speed. Interestingly enough, and this is more for computer science people, the distinction between RISC and CISC, largely unimportant. ARM is a RISC machine. Modern desktop CPUs are CISC machines that then turn into RISC machines as you get deeper into the processor. It's surprisingly not an issue, and it's not something that we have to be concerned about. As far as I'm concerned, it's the compiler's job to deal with that sort of stuff. There are a few architectural oddities with ARM CPUs, which I will talk about. But you can actually run the same code on both desktop and ARM. And this is the result if you run a standard benchmark on a browser, for example. Now, that's the first big caveat. JavaScript browser execution tends to be single-threaded, and that's one restriction. We can probably accept that. It's suited specifically for application logic, which I'll go into later, but basically it means that something like a browser performs very well. And the big one is that it can't be sustained indefinitely. If you keep on hammering your CPU with this benchmark on a desktop, it will keep going without any problems. On mobile, not so much. The performance will gradually tank, and then it will reach a non-recoverable state until you go and let the device cool down, if it hasn't melted a hole in your pocket. But the point is, a modern smartphone CPU is actually pretty forgiving of application code. And application code tends to be kind of object-oriented, very branchy, tends to have a lot of cache misses. Part of the reason for this is that memory is physically close to the chip on mobile, so the cost of a cache miss isn't actually that significant. Indirection, therefore, isn't a big deal, so you don't get the enormous performance penalties of virtual functions that we got in the previous generation of console games. Branch misprediction isn't very problematic, mainly because mobile CPUs don't do as much speculative execution, because we have to bring this all back to power again. You know, if the CPU speculates that you're going to do this and then spends some milliwatts trying to work out what the result is going to be and then has to throw it away, that's much worse for a mobile CPU because you've suddenly got some heat to deal with and you've used up some battery power. They do have speculative execution, but it's not as deeply pipelined as desktop PCs. And so you end up with something that's actually good for complex and OO style code, often with lots of indirections and lots of heap allocations. Browsers and JavaScript are a great example. So mobile phone browsers are pretty good these days, I think we can all agree. But there is a major compromise that they make, and that's the reduced peak throughput. Now, one of the problems with optimization on PC is that you can often end up with an application that has bad data flow characteristics. And so you're actually only using maybe 10 to 50% of what the processor can actually do. Now, most applications kind of by default, especially if you're following like an OO design, will sort of naturally tend towards bad data flow. And that's why a lot of the sort of bleeding edge of optimization techniques is about building better data-driven design and being able to batch up data more sensibly. While you can see huge gains if you rewrite your code to be data-driven on PC, that's not the case for mobile. So if you change the benchmark from a JavaScript benchmark in a browser to something that's data flow optimized, like multiplying a shit ton of matrices, you'll find that the performance is often less than 20% of what you can get on your desktop. Same chip. Even when you're using the native SIMD instructions, such as Neon, and I'm still talking about single-threaded performance, these data flow problems can often be parallelized across multiple cores, and then the lead is basically insurmountable. So that's kind of an overview. I decided to throw in an architectural oddity here. One of the things that a lot of people aren't aware of is that integer divide is one of the slowest CPU opcodes for a desktop CPU. And here are the cycle counts for a Haswell CPU. You can see that adding is 1 cycle, multiplying is 2 cycles. Integer divide comes out as 9, which is, you know, maybe not that crazy, but I threw in CRC32, which was just recently added and apparently is only 1 cycle, which surprised me, and SSE packed float divide, which is dividing a vector of 4 floats by a vector of 4 other floats, and that also only takes 1 cycle. So we can see that there's definitely an outlier here. And the reason it's an outlier is because it involves lots of tables, a surprising amount of silicon, and interestingly enough, ARM didn't support it. They're like, nah, too hard. So it actually falls back to a built-in function in the CRT called udivisi3, which if you actually profile any of your iPhone applications, you can see because it comes up in the instruments profiler because it's got symbols for it, which also means it's not inlined. So, you know, that's extra fun. And that runs a loop. You can look at the source code for it. It's pretty hilarious. So, you know, while it's 9 cycles to do an integer divide on desktop, it's around about 1 billion cycles or so for mobile. I haven't measured it, but that's probably about right. They did actually add it in ARM v7s, which was I think the iPhone 5, but nobody really builds for ARM v7s because It's just an extra target, and you don't get very big benefits, only into the divide, really. They did add it for ARM64, which also is commonly only used for iOS, mainly because the NDK is such a nightmare to deal with that it's actually really hard to build multiple API binaries for Android. Another little thing about ARM chips, they have weak memory ordering. And what I mean by that is that in x86, which has strong memory ordering, if you have a synchronized piece of code, so you've got locks around your multi-threaded code because you're doing it correctly, if one core writes to a variable and then the other core attempts to read it, it's not guaranteed to actually see the write in ARM. So it could see the previous value, even though there is a lock around that piece of code. Which means you have to use fences. Anyone who had to deal with the previous generation of consoles will love fences. We know all about them, they're great. Another strange thing about it, it doesn't actually have built-in atomics at the instruction level. x86 has this nice little prefix you can put in front of an instruction, which the lock prefix, it just tells the L2 caches to agree on the result before you actually return. If you actually want to do an atomic increment, that's the code for ARM. It's a loop where you use load exclusive, you then add 1, and then you try to store exclusive. It might fail, in which case you have to try again. It's kind of like a lock-free code, kind of like a compare and swap lock-free algorithm in C, except this is actually what you have to build those algorithms out of. So there's loops inside loops. Another thing, which if you've been paying attention, you'll probably realize that this only works 99% of the time. Don't forget your fences. So that's a fun problem to deal with when your interlocked code fails just occasionally on some Android devices. So yeah, that's a little aside. But actually the biggest problem with mobile is multi-core, which it's just not realistic on mobile. So FireMonkeys actually uses a multi-threaded engine. We have a split render and update thread. We also have other thread support, but we don't really use it all that much. But the big problem with mobile chips is that they're actually not designed for multi-threaded workloads. And the reason for that is that the TDP, the thermal design power, is basically gated for one core of work. And if you start hitting 2 cores at full power, or even worse, more cores on the devices which have like 8 or something, you will very, very quickly be power gated. And your clock frequency will drop enormously. It's actually exacerbated by this thing called big.little, which is a heterogeneous CPU that's quite common on, well, they just added it for the iPhone 7, but it's been quite common on Android for a while, where they basically jam fast and slow cores into a single piece of silicon. The idea being that you can offload background tasks to the slow cores. Makes a lot of sense. Marketing really likes it because they can say, I've got 16 cores in my phone. I think it is a good idea in theory, but the reality is a bit different. We often find that applications get moved to the slow core by the scheduler, and we haven't yet seen the scheduler ever move an application back to the fast core once it's decided to start scheduling you on the slow core. Maybe that doesn't sound so bad, but the next thing makes it worse. You have to be extremely wary of high clock speeds on mobile devices. I would say be worried once you start hitting the upper end of 1 gigahertz. Some manufacturers are worse than others, but I won't name them. And a good kind of benchmark is looking at the equivalently aged Apple device. See what their clock speed is, see how many cores they have, look at your Android device and realize that it is completely different. The thing is, if you've ever tried to overclock your computer, you might have noticed that you have to very often increase your voltage to get the chips to run faster. But power is based on the square of the voltage, and power is also a direct relationship to the thermal output, because eventually it just becomes waste heat. Which leads to the Android performance fallacy, which is that you might have a 1.8 gigahertz octa-core CPU, but it's not going to sustain that for more than a few seconds. And some Android CPUs are worse than others, like I think the Snapdragon 820 was particularly bad. So are things any better in the GPU space? Well, no. There are multiple GPU vendors, and the driver teams aren't necessarily the same people that build the GPUs. There are also multiple graphics APIs that we have to deal with. Something that seems to be kind of unique to mobile is that we have ridiculous display resolutions. Like, for a long time, your mobile phone game had to run at 4 times the resolution of a console game, and yet you were expected to still make it look good, even though it was handheld and not plugged into anything. Which is exacerbated by thermals again, because at the end of the day, you've got a GPU that needs to work in a sealed and often insulated case. Thankfully, glass cases have started going out of fashion. And it has to be passively cooled. And by passively cooled, I mean it has to put all of the heat in the user's hand. So there are some problems there. Now, I did this table of the kind of 5 main vendors that we deal with on Android and iOS for GPUs. There's the PowerVR devices by Imagination Technologies that use this tile-deferred architecture, which I'll get into. ARM actually builds their own kind of reference GPUs that people use. So Samsung and Qualcomm, Qualcomm sort of appears to have been inspired by ARM GPUs, but they have their own ones. But Samsung uses Mali GPUs, which they license from ARM. And that uses tile-deferred asterisk, which basically means not tile-deferred, but they say it is. Same for Qualcomm Adreno devices. NVIDIA produces devices which are basically like, they take a GeForce 980, and they kind of cut out 1/10 of it, and then they solder it into a phone. So they actually are pretty much like normal desktop GPUs if you're used to that. There's also this group called Vivendi, which Samsung used as a supplier for a bunch of surprisingly popular tablets. We've never actually got any of our games to run on any Vivendi devices because their drivers just don't work. So yeah, you can see that there are a few things to bear in mind with these things. I will talk about tile-deferred rendering, but one thing of particular note is the driver quality. That's something that I'm going to really be harping on about. Drivers on mobile just aren't very good. And they're not good because there are a lot of pitfalls. They often seem to be very badly tested, if at all, and they're very inconsistent. And by inconsistent, I'm really talking about fragmentation. We've all heard about Android fragmentation, lots of different displays, lots of different hardware, etc. Well, there's another dimension to that, which is for the same hardware, there are lots of different driver versions, and some of them will work. Some of them will have horrible, crippling bugs, and some of them will just have the kind of annoying bugs that just halve your frame rate. A couple of examples that we had fairly recently. It turns out that prior to Android Jelly Bean, if you were running an occlusion query on an Adreno 300 class chip, it would just stall the entire graphics pipeline. Didn't even have to ask for the result. Just issuing it was enough to offend the GPU so much that it was like, well, I'm going to finish everything before I even look at that. Galaxy Note 4, another good example where the benchmark said it was actually pretty powerful, but it just took an extra, it was 100% slower to issue every single GL draw command. So that was pretty impressive. There is an exception to this, NVIDIA. They have the same driver team working on all of their platforms. They've obviously got their shit together for PCs for many, many years. It's still the case in mobile. I didn't actually write it down, but Apple produces reasonable drivers. They do occasionally break things. They actually broke occlusion queries at a similar time, which was a very sad day for us. But they fix it in subsequent iOS releases. If anyone's ever tried to deal with Apple bug reporting, if they don't respond, that means it's a real bug, and you still will never know when it's fixed. So, as I mentioned before, thermals are never going to help. Mobile GPUs can get really hot. If you've ever been debugging a game and just put your phone down on a desk and then come back and tried to pick it up and thought, Jesus Christ, PC's hot. Yeah, it's a real problem. And the thermals will cause the power gating and the thermal sensors to trip. You'll get clocked right down very quickly. Another kind of curious thing about mobile graphics, vendors really don't seem to like providing any kind of documentation. On console, you would get cycle counts and like deep information about kind of how the architecture works. Mobile, not so much. They don't really want you to know at all, and they tend to just deflect any questions when you ask them. So I said I would talk about tile-deferred rendering because it's probably the biggest difference between mobile graphics and PC graphics. So the purpose of it is basically to reduce power usage. Much like how the ARM chips don't do very much speculative execution, this is really a way of lowering the amount of work that the GPU has to do to produce the correct result. It does have macro performance implications for us as game developers that are worth remembering. And like I said before, Qualcomm and Mali have, they say in various places that they have a tile-deferred system. Their tiling seems to be more about fitting stuff into the video memory and less about hidden surface removal. So the performance characteristics are totally different, not really comparable. Talking about not comparable, the architectures of your sort of typical desktop GPU and a PowerVR GPU are actually pretty uncomparable. A GeForce 980 has 2048 shader cores divided into these streaming Maxwell processors, or whatever they're called, SMMs. And you can see over there, that's a PowerVR block diagram for a Rogue, which is used for the iPhone 6S, and it has 6 cores. So that's a lot of difference between the two in terms of orders of magnitude. So something has to be different about the architecture. Now, on a PC, they're really hyper-optimized for throughput. Work is divided into independent jobs, and so as the command buffer processes draws, what happens is that it will dispatch job to the vertex shaders, to individual shading units. I've gone for a kind of, the way I'm drawing this is not entirely accurate. If you work for NVIDIA or someone, sorry, it's close enough. But basically, the vertex shaders are all dispatched as individual jobs. They output to the rasterizer hardware, which then will redispatch pixel fragments back to the shader cores to deal with. And so you have this mixed workload of vertices and pixels in parallel, and the shader cores will basically crunch through blocks of pixels or chunks of vertices at once. You can also be working on things that are unrelated to the current render target. Basically, it's just a giant job system implemented in hardware. This doesn't work so well in mobile because it might do extra work. And by that I mean we could potentially be rasterizing pixels that are never seen because they're behind opaque geometry. And that's why the PowerVR hardware uses perfect hidden surface removal, because they said, well, we don't want to spend our precious battery power on that, so we'll change the way it works. In PowerVR, the command buffer processes draws, and it invokes the vertex shader for each of its shader cores, and they output to a ring buffer. Now that ring buffer contains all of the post-transformed vertices, as well as topology information and varying information. The rasterizer will then determine which tiles are affected by each polygon. And after all vertices are processed in a scene, then the tiler will identify which pixels actually need to be shaded. And then tiles get dispatched separately. So you can see there's this kind of barrier in the middle, which does actually have quite significant performance implications. But what it does mean is that these devices punch above their weight when it comes to opaque geometry, at least. The advantages, it is much better at rejecting pixels than High-Z, which is what is used in desktop CPUs. There's also a lot of per-pixel memory inside the tiler itself, which you could potentially use for kind of mobile designed deferred rendering if you wanted to. And of course, power usage is lower. There are some drawbacks though, and that is it can only really process one kind of scene or render target at a time. There is a single shared buffer for all of this post-transformed data, and extra varyings add pressure to that buffer, and once you've used up that buffer, it has to do a complete flush of everything and then start again. This is called a split scene in iOS. Thankfully, they're very rare, and you have to be throwing huge numbers of vertices at the system to actually see that. There's also a very large cost to load and unload the tilers with the current render target information, which basically means that you should be extremely wary of kind of rendering half a scene and then switching to another render target, rendering that, and then going back to the first one, which unfortunately seems to be something that people try to do quite often, even when the engine tries very hard to stop you from doing it. And there are also some other special cases. Alpha blend, kind of by necessity, needs to cause the tiler to flush, because otherwise you won't have the order maintained and it just won't make sense. Alpha test, however, basically causes the tiler's hidden surface removal to switch from a planar equation to an individual pixel level, and that slows it down significantly as well. A final note about the GPUs. Don't believe the benchmarks, especially GL benchmark. And it is possible that some manufacturers might be cheating a bit on the benchmarks. So yeah, I'll just gloss over that lest someone send me some angry emails. So a couple of kind of opinions to kind of sum up those last two bits. In my opinion, mobile graphics is still a long way behind PC and consoles. The tile-based deferred rendering and the unified shader cores actually tends to make vertex shading quite expensive, because the shader cores are really designed. You've got 6 cores that are designed to process something like 4,000 pixels or something at an incredible rate, and then you're starting to actually put complex vertex shaders in them. They run a lot slower. But conversely, the fact that the fragment shader has to run at such a ridiculous resolution means that you actually end up more fragment bound than anything else. The problem for me as an engine developer is that I can't predict the performance a priori, not even when you give me the device specifications, because the drivers are so inconsistent. And at the end of the day, it means that we have to make a lot of compromises when we ship a game. Like I said, fragment operations tend to be the big issue, so post-effects in particular tends to take a really serious hit. So now we'll go into our most recent title, Need for Speed No Limits, which shipped last year, I think. We've actually got someone in the team, in the audience. It's actually quite a graphically complex game. We have a very variable workload between 100 and 1,000 draws per frame, fully dynamic shadows, real-time cube maps that are being rendered from the camera's position every frame, and we target 30 FPS. If you try to do a serious mobile game, serious being with lots of graphics, don't even aim for 60, it's not realistic. It's fairly heavy on the CPU usage, mainly because it's got quite a sophisticated physics engine. We're actually using Havoc. And we target iPhone 4S class hardware and up. The thing is, that's actually 2 orders of magnitude of device power. So we had to put in a whole lot of tiering settings. And in fact, Need for Speed uses an online tiering system where it will download options the first time you run the game, so that if we see lots of reviews saying it's really bad on my phone, we can just go into the tiering options and turn things down. And then hopefully the reviews will go away. But arguably, we added too many tiering settings. So, but it does run on all of those devices. There are a couple of kind of observations I have about the process of shipping Need for Speed. I think it's unlikely that games are going to be CPU limited on mobile devices. Like I said, we use quite sophisticated physics simulation. That adds a certain degree of complexity, but you can get away with a lot of stuff on in your game update. that's not an excuse not to optimize your code, and it's not an excuse to use the wrong type of algorithm when you're doing anything, so you're not off the hook entirely. With the tiering options we put into Need for Speed, they were entirely about reducing the draw calls. And that was mostly about drivers. So particular devices that we know had particularly slow drivers, we would change the tiering options to reduce the draw calls. But they also have a kind of secondary effect. Draw calls require the renderer to do a bunch of maths to kind of position things and frost and color and all that sort of stuff. That's the sort of thing that I previously said these CPUs are actually not very good at compared to PC CPUs. So by reducing the draw calls, we also reduce that pressure. The other caveat really is that code that you don't control may be very badly written. Drivers, Qualcomm, etc. The other thing is phone OSs are multitasking. So when you're thinking about the performance of these things, you have to bear in mind that your application may, of course, be context switched away while the phone does something vastly more important, like sending all of your contact details to AdColony or something like that. And you have to be extra careful if you have a multi-threaded engine. So a couple of CPU optimization tips, which I thought I'd just throw in here. Make sure you're using Neon if you're able to. I mean, obviously, you people with Unity, you don't control these things, but Unity does use Neon, so don't worry. Some people think that you should use OS, which is the compiler flag optimized for speed. I don't actually think that flag has been useful since 1986. Hello? Size, yes, that's the bad one. Don't use OS, it's terrible. Because it's much better to inline everything and just have more code. It will execute a shit ton faster than less code. The instruction caches tend not to be a really obvious thing. I'm going to give you the 3 rules for optimized code that we use in EA FireMonkeys, so bear in mind these are trade secrets. The first one is that you should write good code. Failing that, because one is basically unachievable, try not to write actively bad code. And the big one is avoid allocations. So, sorry, Unity people, you're all SOL from now on. But if you are a native developer, please don't allocate transient data in the middle of your frames. It's just awful. Please stop doing it. So back to NFS, most of the actual tiering options that were useful were on the GPU side. The biggest impact was being able to control the resolution. So Need for Speed renders the 3D scene and then composites the 2D scene on top. Originally, we just thought, well, the 3D scene's got all of the complex shaders, that's going to be fine. So we could scale that up and down and change the compositing. It actually turned out that certain phones really had insane resolutions, like just ridiculous resolutions. And even our simple UI shaders that were just like draw alpha blended quad were taking up the majority of the frame. So we also added support for changing the Android native window resolution, which is something you can do since Android 5, I think. And that basically means that the hardware will then do an upscale composite for you, and we can render our UI at a lower resolution as well. That is the single biggest thing that we do to control the frame rate on Android. Another big impact thing is the use or absence of post effects. Need for Speed has something like 6 or 7 post effects shaders that could or potentially couldn't be active at once. Every time we add an additional full screen pass, it's just bad. The Tyler architectures don't like it because it means they're going to have to flush all of the data out. The rest of the phones just have, insane resolutions, which means you've got to deal with that. So it's a problem. Something that had a kind of more variable impact was the complexity of shaders. It's often very hard for us to measure due to the the difficulty in profiling and really getting stable results out of these devices. Need for Speed's shaders are very highly tunable. The engine that we have actually doesn't have pre-built shaders. It dynamically compiles a shader graph at runtime. So we can quite easily change it and kind of remove detail settings. So we have about 20 parameters in Need for Speed in the road shader. And that's probably the most expensive shader in the game. It's very hard to see whether the cost is coming from ALUs, which is just shader instructions. The pressure from varyings is another big thing that's very difficult to measure. And also texture cache pressure, which isn't something you really see on PowerVR devices. I think the Tyler has special magic for caching the textures, but Adreno chips in particular, they don't like sampling non-compressed textures. Another thing that we discovered, we actually had someone from Samsung come down and talk to us when we were working on Vulkan, which I'll talk to at the end. We found out that we were able to massively improve the thermals of the game by switching a bunch of our fragment logic to FP16 rather than FP32. This might sound really obvious to people who have worked in console, because everyone always does their pixel shaders as half precision. We've actually had this kind of unusual situation where we started with mobile, and then the PowerVR devices perform at full speed, at full precision, and iOS 5 just changed the shader compiler to kind of upcast everything to high precision anyway. It was all very strange. So since then, we all kind of ignored precision and assumed it was great. Turns out it isn't. Some other things, draw calls, variable impact, very dependent on the hardware and the driver and the actual API that you're using. iPhones don't really seem to be terribly affected by draw calls ever since the 5. Android devices, complete opposite. They really hate draw calls. Not sure if it's because the CPUs are just downclocking so much or because the drivers are so bad, sometimes both. Couple of other things. Like I said before, watch the use of full screen effects. We have a falling rain effect, which is a cylinder around the camera and does 3 texture samples so that you can get 3 parallaxes of rain. That takes 5 milliseconds to render on an iPhone 5S, which is enormous. That's like, a sixth of the frame. So we turned that off. The other thing is that UI artists really like the way that Top Gear looks. So if you're making a racing game, they keep on trying to shove vignettes in the game, and they do that by putting a big full screen quad over the screen, and then the performance tanks. So keep an eye on them. Tyler memory, like I said, is a big issue, so make sure you use discard frame buffers and avoid switching your frame buffers. And alpha and alpha test we've been using the phrase poison the Tyler, which I did actually say to a PowerVR person, and he was very confused and slightly offended that I used that term, but it's a pretty accurate description of it. If you have any tiles that are covered by alpha-tested geometry will perform badly until you change render targets. That's just how it is, and significantly badly. Also, alpha-blended geometry causes flushes, which means that you basically have all kinds of strange issues where in a previous Need for Speed, we actually had the garage as a sort of semi-transparent, the floor was just semi-transparent, and we rendered the car again underneath to make it look like it was a beautiful mirror. That the order of rendering basically changed the frame rate by a factor of 50%. So if we rendered the car on top first and therefore occluded all of the pixels that were underneath the car for that alpha blended floor, and so the depth test could just discard them trivially, we had a frame rate of 30. If we rendered the floor plane before the car on top, so there were some pixels that were going to be alpha blended and then covered by opaque geometry, we had a frame rate of 15. That was on an iPhone 4S. So pretty significant changes. Just a little thing about our engine. So about 5 years ago, we moved to a split render and update threading model. We also added a job system just to try to make it kind of modern. We do not use the job system. And we don't use it because every time we try to use it, the devices start falling over. So we stay very much in the render update threading model. We've got some other threads, but they do much less work. So, last real topic. There's a bit of a trend for high-performance graphics APIs. What are they? How do they differ from OpenGL? And are they actually worth it? So these are the 3 APIs that are available in mobile. Actually, these are also the 3 APIs that our engine supports. You might ask what low-level actually means. I've done a very, very suspicious chart here. As you can see, OpenGL has an abstraction depth of 50, and then you can work out the rest. Basically, it's a measure of driver overhead. And the lowest level APIs give you direct access to a command buffer that the GPU interprets directly, sort of. It's a double-edged sword because driver authors, at least on PC, and certainly NVIDIA, even on mobile, kind of look at what your application is saying to the rendering API as a suggestion, and then they kind of reorder it to actually perform well. Low-level APIs, you don't get that kind of safety net. You have to do it right yourself. You typically get direct access to the resources, which is obviously very suited to the unified memory architecture in mobile. But you tend to need to write your own manual fencing. So if you render to a texture and then you want to use that result, you've got to make sure that you've fenced the instructions so the GPU knows actually you might want those pixels to be done before you start sampling from them. Same with dynamic geometry and also even the vertical sync and dealing with the presentation blank. Another thing which some people strangely don't seem to realize, shaders aren't going to get any cheaper. If you're bound by ALUs or the physical hardware like texture cache, low-level API isn't going to save you. Sorry. Just to go into the specific ones, Metal, it's a fairly explicit API. I actually like Metal a lot. I think it's a lot like DirectX 11, which I think is probably the best designed graphics API. So if you're interested in that, play around with DirectX 11. Fencing semi-automatic, it kind of mostly works most of the time. I would say it's probably not particularly low level. Like I said, it's like DirectX 11, which isn't meant to be a low level API. And that's really more a case of OpenGL ES giving us an unrealistic expectation of what a graphics API should be like. There are some drawbacks. The Metal shading language is very strange. It's entirely through Objective-C, and it will create extra threads for you, lots of them potentially, if you're using it not the way that they expected. It did give us a fairly large performance boost on the devices which supported it, which unfortunately were the devices that didn't need it. But, you know, reduced the draw call cost by about 60%. The extra threads, not a big deal on iOS because Apple tends to have fairly well-clocked devices, and so the thermals are much better. We also have to cache some of the Metal state in C++ to avoid the overhead of Objective-C. So the first implementation of the Metal renderer, we spent 5% of the time accessing an Objective-C property of the entire frame time, which is pretty special. Verdict, A-, we'll implement again. Vulkan, very low level, potentially very performant, much closer to the command buffer. The draw calls are extremely fast. They basically just memcopy a thing into a command buffer saying, hey, draw this stuff, and that's it. It also has GLSL shader compatibility through various Blackmagic means. But it comes with drawbacks. The drivers are horrific. There are many, many Vulkan driver revisions. They are pushed over the air at a sporadic rate, and they're completely different for every single piece of Vulkan-enabled hardware out there. And you can't tell what the driver version is. You can tell what the Vulkan version is, not the driver version. Manual fencing for everything means that there are a lot of arcane API calls. And so we have a 700-line class in our Vulkan implementation, which basically does EGL swap buffers, just because there is so much stuff to make sure that the rendering is done and that the frame buffer has been converted into a format that's presentable and that it's synced with the VBlank, etc., all sorts of things like that. It's very, very verbose, very, very fragile. There's little or no debugging support, and these combinations mean that you spend a lot of time staring at a blank screen thinking, what the heck is wrong with this? That was 3 months of that, which was great. There is actually a Vulkan debugging layer called Vulkan validation, but it doesn't work. We have seen enormous performance gains with Vulkan, and I think as the drivers get better, we will see even better gains. But there are lots of issues, and we actually implemented Vulkan for NFS in May. Google I/O, we demoed it. We haven't shipped it because we are not confident that the devices that people actually have in their sweaty palms have the correct Vulkan drivers, so it's all been turned off. give it time. Overall, should you implement a low-level API? I would say no, unless you work for an engine team. And I have been writing 3D engines in my spare time since high school. Metal, if you're an iOS or Mac person, that's an exception. I think it's good. If you're not an iOS or a Mac person, DirectX 11, learn that. The gains are good, but they do require a lot of effort. And now my final surprise slide, VR. So we've announced that we're developing a VR title for the Google Daydream platform, which is a Need for Speed game. You can't target 30 hertz. You really have to target 60 hertz unless you want everyone to feel very sick. Surprise, thermals don't get better when the device is on your face. And we haven't shipped yet, and we're in the optimization stage now, and it is an uphill battle. So we've had to make very serious graphics compromises to hit frame rate. The cost of draw calls is killing us. Google's own recommendations are less than 100 draws for both eyes, and we're trying to get Need for Speed in it, which is like 400, 500 draws. It's difficult. We are investigating some extensions like the Oculus multi-view extension. I'm actually going to be, when I go back to work tomorrow, I'm going to be continuing this. My experience hasn't been great. On one device, it doesn't work, and on another device, it reboots the phone. So we'll see how that goes. And that's it. So, yeah.